This is a production of Cornell University.
And thanks everyone for coming on Thanksgiving. Before I get into what my talk is about, I did have a little slide that maybe I can navigate to. You just described. So I'm actually from Utica, New York. Yeah, you guys probably know where Utica is. And I initially went to school for construction technology back in '08 and decided I really wanted to work outside in construction. They put me in an office and I estimated construction jobs and I wanted to get out of doing that. So then somehow I ended up doing physics at Brockport. This started my sort of imaging journey with Hubble Space Telescope imagery. And then when that was done, I went out to Idaho. And if I'm an expert in anything, you're going to get a lot of disclaimers during this talk about what I do and don't know. But it was planetary rings and their interactions with moons and the magnetosphere and the interior planets, but I don't do that anymore so much. When that finished up, I moved to Rochester. My wife is from Rochester, so we wanted to settle down there. And sort of as a backup, I did this imaging science program as a master's after my PhD. And that's when I first started getting into these projects that deal with agriculture. So all these little things are different projects and funding sources and things. But what I do now in the imaging science department is work in the digital imaging and remote sensing lab. Is sort of, we call it research engineers, but I'm not an engineer. Here I would be like a research associate or research scientist, soft money research on various things. Some of my stuff is ag, some is forestry. Last week I was in Palau, a small island off the coast of Philippines, in mangrove forests, measuring mud with a colleague of mine at the Forest Service. In a couple of weeks, I'll be at AGU talking about a mission to Uranus. So like I work on totally different things. But disclaimer and first excuse, I'm not an expert in agriculture. I'm not an engineer. What I do is I turn imagery into information with a lot of skepticism, usually. Just about RIT and imaging science. So this was RIT's first PhD program back in the late 80s. They preached the imaging chain. So following, the light source, hitting some object, interacting with it, reflectance, transmission, absorption, viewed from some imaging system and collected through the optics. Those photons hit the sensor, turning those digital numbers into radiance and in our case, reflectance, through processing, doing things like computer vision to turn that actual image information into some kind of information. There's people into displaying and, how do we display things with the right colors? There's this whole color science field that I honestly don't know much about, but people learn that in our department. And then perceiving like both the real world and screens and like how our brains process the imagery and how we make better images and things like that. Within the Center for Imaging Science is the Digital Imaging and Remote Sensing Lab. So you see this logo throughout my talk in the upper right. You turn on I'm using my mouse and you can't see now you can see. So yeah, Digital Imaging and Remote Sensing Lab. So there's 12 affiliated faculty, 12 staff researchers, of which I am one, and then about 50 undergrads and grads typically in total working on DEERS-related projects. We're probably the bulk of imaging science in terms of research funding, about 3/4 of that, and about 1/3 of the College of Science as a whole at RIT in terms of research funding, which these numbers probably aren't that big compared to Cornell here. About pretty steady for the last several years, about $4 million a year, which I'm finally starting to contribute to. So now you have my background and a little bit about RIT. I don't know if there's undergrads here, but if you're interested in remote sensing, you should just Google RIT DEERS. There's great annual reports on all the research being done there. Or if you have children that want to go, I don't know. I got to do my plug for RIT. So yeah, 5 years ago now, I was a master's student in imaging science, and I was attracted to this agriculture-related project. My professor, Jan Van Aert, was a part of. It's a huge group of people, a lot of money. This is Specialty Crop Research Initiative, funded for, it eventually finished up this year. We got the 1-year extension. About $5 million. RIT was about 350K of that, so like 7% or so. Marcus Keller at Washington State University sort of led and managed the team. The main problem was, vineyards are variable. How do we mitigate that? How do we get a regular, continuous, happy, healthy vineyard? This is out in Washington. I don't know that we have these problems here. So this yellow is pretty severe nitrogen deficiency. Those are some problems they have out there. It's obviously not a climate that's conducive naturally to support these plants. So they do a lot of fertilizer amendments and things. But the whole point is we want to be able to do that in a more intelligent way, not just apply, the same prescription across all that acreage. We want to give the plants that need it the most, the good stuff, and stuff that's already doing fine. We don't want to waste. We don't, both for money's sake, but also we don't want to contribute to, adding these harmful inputs to the water supply and prevent algal blooms in the Finger Lakes or Great Lakes and stuff like that. So that's the main motivation for this work. It's a big team. So this had people at Washington State, Oregon, University of Oregon State, UC Davis in California, Cornell, RIT, Virginia Tech, all over the country, all the different types of grapes for different production purposes, and including wine, juice, table, raisin, and then we had different focus group teams. So I was part of the sensors and engineering team, and our mandate was to develop a non-destructive near real-time sensing tool to measure grapevine nutrient status across the vineyard. We've pretty much been able to do that the whole time, but can we do it better? Was our main goal, and could we do it in a way that satisfied the advisory committee? It's another question. We worked hand in hand with the precision management. We'd make our predictions for nitrogen and potassium and things like that, and they would develop a management solution taking into account other layers of information about the vineyard. And people in the plant nutrition and product quality section were interested in really exploring what do these different amendments do based on the nutrition levels that we see. How do we tailor our amendments to get the desired result and come up with these sort of threshold values for deficiency? And then a whole wing of social science and extension. So outreach through extension, a podcast, and actual people looking at economic impact of if you do address vineyard nutrition, what gain do you get? Every year we would meet for like an annual checkup with the advisory group, which was wine growers and winemakers, sort of steering the ship, making sure they were happy with what we were doing. And over time, the message was they want their effing sensor. Like, that's literally what they said every time. They want the sensor that works and does this, which is very frustrating to me to hear, because I thought we were doing it the whole time, but something was sort of lost in translation. And then the other issue was always this debate that eventually happened between measuring the stems, the petioles of the plant versus measuring the leaves. And there was never a solution to that. That wasn't part of my argument, but that's what happened throughout the time that I was there. It seemed like the meetings always developed into that. I'm not sure what that has to do with the slide, but we did a lot of these things. This was the method. And then if you want to check out the results of the project, you can check out the website. They're on social media. There's 25 podcast episodes with various people on the team, including industry folks. But again, our mandate in the Sensors and Engineering group was to deliver this sensor and these various other ambitious goals, which I'm going to skip through. Our team at RIT consisted of my advisor, Jan Van Aert, at the time. He was one of the co-PIs, of which there were a dozen or more. Myself as a student, and then as a postdoc, and now as staff. And then we have a drone team at RIT. So within the Deers lab, we have a whole drone lab with a couple different integrated packages with a whole bunch of different sensors, including LiDAR, multispectral, hyperspectral, thermal, you name it. They often put them on these all on a single drone, which means it's kind of like, can take all the data, but it's not super tuned to doing any one of the measurements at once, but that's what we have, and we've flown throughout the project. So now, with that sort of preamble, some background on actually sensing nutritions and the prospects of this. So what makes up the plant matter, right? This is actually from our samples, our dried samples. We'll talk about that more in a little bit, but I thought it was a good figure to show. So most of the dried leaf sample that we send to the lab is just carbon, hydrogen, oxygen. It's not the stuff that we're particularly interested in for this. We're interested in those mineral nutrients, NK, P, etc. Of that, 6% or so mineral nutrients. Here I'm showing the bloom and the Vray sun. So this is like early June versus late August numbers on our samples. Just 6% is that mineral nutrients. And of that 6%, most of it is nitrogen, about half of that remainder. And then, you can see the numbers here. Calcium and potassium make up the next highest amount. And then these are vanishingly small. So we're talking about trying to use a sensor, remote sensing, to measure this really small number, really small change in the plant. And this is a dried sample, mind you. What we're looking at with our sensors is the wet leaf that is mostly water, so it's even more percentage of this. Nitrogen has the highest amount. It's the best target. We know there's spectral features in the visible to shortwave infrared spectrum that are due to nitrogen. So it's probably the best target and probably the most valuable. Maybe not for upstate New York concerns. I think potassium's the bigger nutrient desired, but out west for sure, nitrogen is super important. And our understanding of foliar chemistry hasn't really changed. So these are two papers from the Journal of Remote Sensing of Environment, one a year older than I am, and then one from 5 years ago by some renowned authors. And this table is from the one on the bottom, citing those numbers that they found in 1989. So these are the wavelengths that are important if you want to measure nitrogen in visible to shortwave infrared spectra of leaves. And they haven't changed, they're the same. And it's still just as hard to do as it was back then to a certain degree. And again, these are coming from dried leaf spectral samples where they're actually able to measure this. It's really hard to do out in the field. If anything, we're measuring, small changes in the nitrogen having some downstream effect in the appearance of the plant due to however it needs to use the nitrogen. So an unfortunate reality is that existing affordable sensors are not really sensitive in the shortwave infrared. They're useful for the visible and the near infrared, but extending out, they don't have the sensitivity. These often require more exotic materials that need to be cooled to get you good data. There's a whole bunch of problematic things with imaging in the SWIR as well. But that's where these features all lie. So the shortwave infrared is like, 1200 and beyond, or some cutoff. So most of these features for nitrogen in particular, the one that we have the most promise for, live in an area that's hard to image in. There's long-standing and well-understood relationship with chlorophyll, but it's not perfect, right? Like a lot of things can cause chlorotic symptoms in plants, not just a lack of nitrogen. So sometimes, there's hundreds of studies out there using remote sensing to model nitrogen, but we don't have a unified model for a reason. The problem isn't really solved, right? can have a study and the model looks good, but if you apply it to new data it hasn't seen, it's not going to necessarily work great. So that's a long-standing problem. This is just showing that same thing in a different way. Here we're actually showing the visible to shortwave infrared spectra. I'm showing two different ones. The orange is coming from our imaging spectrometers on the drone, and the black line is, the best spectra you can get from this leaf clip spectrometer here. So you're actually illuminating, in a closed environment, the leaf with known light, measuring the reflectance in real time. And then I'm sort of mapping on here the various signatures from those tables above, most of which live in the shortwave part here. So all these big dips, that's water in the plant. So we're looking for these vanishingly small absorption features in these giant dips that are sort of obscuring them. So this is a really hard problem to do in terms of measuring directly. And that's why the best that we've been able to do is develop these cursory relationships with chlorophyll, right? And it lives in this nice silicon sensor range with cheap sensors. So we're good at doing this, but it's not perfect. Further caution on spectral imaging and machine learning for this type of thing. So as I said, there's no shortage of papers about using drone data or remote sensing data to do this kind of thing. But is it really helping us? This paper came out in 2024 and rang true, and my paper is probably one of the ones that it's complaining about, and I'm right there with them. Having a generalized model for this is really hard. It's not as simple as something that you could see and you can measure in the imagery. It's like some downstream subtle effect that you're seeing due to these changes in the nutrition levels. Yeah, so it's a hard problem, but I think there's some hope. So faced with these challenges, what have we accomplished? Mainly, we've thrown the kitchen sink at it in terms of different sensors, modalities, and resolutions for looking at vineyard nutrition. We're comparing measurements made at bloom to measurements made at Vracen when the fruit is ripening, and investigating sensors across multiple seasons, and started to think harder about the other data layers that we're adding into the mix to be able to get a better picture of nutrition in the vineyard. So I'm going to get into some of the data. Our main study sites were out in Western New York, off the coast of Lake Erie at the Cornell Lake Erie Research and Extension Lab. So we coordinate a lot with Terry Bates out there. I don't know if any of you know him. In these two vineyard blocks. So most of our data comes from this small 1 acre block that was actually sort of newly established, and they attempted to induce deficiency in it. And then we sort of always also imaged this 7 acre block up here that was more commercially managed and had sort of the run-of-the-mill problems that the vineyards have. But the majority of our samples came from this bottom block here. We imaged from 2020 in the fall when the project started, all the way up through the end of last year, with various subsets of our imaging data and various sampling regimes. But generally, we got 100 samples out of this smaller block. So that's what these little squares are showing. I'm showing potassium for no good reason. We did vine level sampling. This just shows sort of their attempt to induce deficiency from the outset in this block. Just showing that, we had a subblock where they were trying to induce a deficiency in nitrogen by limiting, the nitrogen input, a control that was supposed to be healthy, one to induce potassium deficiency, and this sort of low pH one, the sort of goal of reducing magnesium content. So the sampling, like I said, was vine level. They would take 50 leaves and 50 petioles and separate them into separate bags. And so 50 leaves and 50 petioles coming from the same vine, send that to the lab. So you'd have like a vine level information on nutrition, both in the leaves and the petioles, because there was a big discrepancy about which one we should use. These are the details about lab processing and the prep and things. The big point I want to make here is what they actually got from the lab. And not being super familiar with agriculture before this project, they give me the target that I'm supposed to calibrate to with my imaging data, and I just took it. I didn't really think much about it. But this is actually really important, that what they were giving us was a concentration, right? They were giving us the milligrams of nitrogen per kilogram of the original sample. But this says nothing about the size of the vine that it came from and how that concentration is sort of diluted across of a bigger or smaller vine. And that's going to play a bigger role later. But this is what I spent the majority of my time trying to build a model for. As far as imaging data goes, this is on the left is the main, probably most of our data came from this drone, including LiDAR, multispectral. So this is 5 bands, blue, green, red, near infrared, and red edge, which is sort of this region where the reflectance of vegetation shoots up. Also hyperspectral imagery, so just the same kind of thing, but hundreds of bands spanning that region. And then we had a twin drone that had a cooled shortwave infrared sensor that extended this out to 2,500 nanometers. And then later in the project, we got this cheaper multispectral drone with 4 bands that could pretty much do the job of this camera on a much smaller package that's more translatable to maybe a grower going out and using it. We also collected satellite data from Planet Labs. It's 3-meter pixels. Again, visible to near infrared, multispectral, 8 bands. Anyone can grab this data. It's near daily now. At the start of the project, it wasn't quite there yet. But anyone, I should say, that has a university login can go sign up for 500 or 5,000 square kilometers a month. Have fun. They now have hyperspectral, not at this temporal resolution, but maybe in the future. Out at Clairel, Terry also has the system that measures in-field NDVI with this Holland crop circle active canopy sensor. So we have that data throughout the course of the project. I also compiled Sentinel-2 data. So this is from the European Space Agency, so public, free data. The 4 Wiener bands are 10-meter resolution. They have other bands at coarser resolutions as well, with about a week temporal resolution. And then I also, we probably won't get to their impact here, but I also collected soil data, so that's unchanging for the field. And Terry actually collected soil electroconductivity and magnetic susceptibility for his vineyard every year, though it didn't really change, in terms of its relative level. So we incorporated that. Elevation ended up playing a kind of a big role. That's free to grab as well, and we actually get it from our drone data too. And then explored weather data a bit, since we're talking about multiple years, different things going on in terms of temperature and precipitation. So to dig into the data a little bit. So this is just looking at those leaf versus petiole concentrations that we're getting for nitrogen. I'm showing his green points are from bloom, so early season, and the orange are late season variation data. I said earlier that there was a big, kerfuffle about what we should use. From a remote sensing perspective, I'm looking at leaves, right? I'm not looking at the stems. So that made sense to me. The trouble is that the thresholds from the literature are all petiole numbers. So there was a long-standing protocol to measure the stems and get the lab analysis for those. But what I'm seeing here is a pretty linear relationship between the two. Maybe more so at bloom than at veraison. But you can, make a cursory linear relationship between these and convert between the two. So I could take those thresholds that they have for petioles in the wine grape production guide, convert them to leaf numbers, et cetera. It turned out that most of our data samples weren't deficient over the course of the project. So the deficient I'm showing is the solid red line. For the commercial block, that one we sampled less frequently, we had a good amount of deficiency samples. But for the ones where we were actually like measuring every year and really trying to induce deficiency, we didn't really achieve that. For bloom time, almost at all, really only at Sun were we able to see those effects. Another point is that, so this is actually from the wine grape production guide in the appendices. This is their management decision, right, for nitrogen. So they're using, again, those concentration numbers from the lab at bloom in this column, and then this days after bloom is like Sun, basically, so end of season, for the different thresholds. But all these thresholds come with a qualifier. They're all about vine size. So like, which makes sense to me. More nitrogen, bigger, more vigorous vine, right? Is sort of, I don't know. That's what makes sense to me. So why aren't we incorporating that information into the model? Why am I trying to model with my remote sensing these concentration numbers that can be, I have two vines that are totally different size but have the same concentration of nitrogen. So it's like a bad target. That's all I'm trying to say here. And it took me a while to really realize that. But you'll see the role later. This is just showing the trends in our actual ground truth samples of those concentrations over time. So on the top is all our bloom data for that block. On the bottom is all the racin. The green rectangle is just showing that sub-block where there was an attempt to induce the deficiency. So in both of these, the red points are actually deficient ones by the threshold. So you can see at bloom we had almost no truly deficient by the threshold vines. But at Sun, we succeeded in having deficiency in most of the block, actually. Shifting to potassium, a little bit different than nitrogen. So the relationship between the leaves and the petioles is pretty consistent over the course of the growing season. So both the yellow at Sun and the bloom points are pretty consistent. Though we didn't see many deficient potassium vines at all, you could see the deficiency for both bloom here and Sun with the solid line. Very few samples end up on that left side, and most of them are coming from the commercial block and not from our study vines in the green. And here, just showing those trends. So here, the red points, at least on the top, we didn't have any deficiency or any below the deficiency. So it becomes hard, right? Like if the vine isn't deficient, is it going to show symptoms of deficiency? Probably not, right? So are we going to be able to detect that? I don't know. I think it's a little dubious. If for Sun, we have more examples of deficiency develop over time, for sure. All right, now to get a little bit away from the nutrition data into like the actual remote sensing data. So here I'm showing 3 different modalities. On the left is satellites at 3 meter pixels. In the center is about 5 centimeter pixels coming from our drone, and then on the right is field data that Terry took with his in-field NDVI sensors. So these are all NDVI. So they're all measuring the same thing, right? But no, these are all different ranges. And the reason for that is, this pixel is mixed. This pixel has all the content of this, including the ground, the vine, the inner row, grass, everything. Only in the drone imagery can we actually extract spectral information specifically from the vines themselves and ignore everything else. So you're not getting that with the satellite data, even though you could sort of see the same pattern throughout the vineyard, right? Like at these red areas in the satellite image, we have this sort of sparser, you see more red soil points in the drone imagery, and in this particularly green spot where you don't see much of the soil, those red points in the NDVI space, you have this big green blob over here as well. So that makes sense. But really, if you want to be able to turn spectral information from the vine canopy into an estimate of the vine nitrogen, you probably want the pixels that are corresponding to the vine themselves and not this background information. But this does tell you something, right? Like these lower values are telling you that there's less vine there, right? Because the highest NDVI stuff is the vine themselves. So if there's a lower number here, that's probably telling you that there's less vine taking up the pixel, which maybe that's telling you something about nitrogen too. Just a deeper look at that. This is the same area of one of the vineyards, and I'm sort of masking in this checkerboard pattern at Bloom and at Veraison, the same area of the vineyard. So you can see at Bloom, wimpier vines, and then by the end of the year, they're, very lush. And these squares are Sentinel 2 size pixels, so 10 meters, and just the different percentage of actual vine content in them. So at Bloom, it's even less than a quarter of that Sentinel 2 pixel is actually vine material. A lot of it's just background stuff, grass and dirt and whatever else. At Veraison, it gets up to about 50%. But a wider, play there as well, like this one in the lower right, that has, narrower vines. It's a bigger swing than what we see here. Spread, sorry. So it's just something to keep in mind when you're thinking about satellite data versus drone data, and the power you have with the drone data to be able to actually extract spectral information from your target and to be able to assess the size of those vines, which should have some role in measuring nitrogen as well. So how we would go about modeling any of these nutrients is take all of our image samples, the locations where we measured nitrogen or nutrients in the field, and extract just those pixels corresponding to that vine, and all the related image products that we can generate. So for one of our study vines, we'll mask out anything that isn't the plant itself, get an average reflectance for each of the bands that we're imaging in. We can turn those into vegetation indices. We can, you can count out the pixels. We know the resolution. We can determine the area. We have multiple views so we're able to extract height information, right? Like when we fly over the vineyard, we take images from multiple perspectives, so you can infer depth and be able to extract information like height. So we can get some more richer structural information like canopy height, even estimate things like canopy volume. And we can also plug in some of those other layers like yield, elevation, soil, what have you, and then pick a target. And basically we're just running any machine learning model you want to try out on that with all of our imaging data with the nutrient target. But again, we were for the longest time held up on calibrating to these concentration levels of the various nutrients that we got back from the lab, which I don't know. It took me a while to figure out why that was such a problem. This is just sort of showing what I was saying, how we fly our drone. Part of the standard processing is creating these 3D reconstructions from which we can extract rich structural information. So here I'm just pulling out the volume of each of those vines and mapping it in GIS. So this was sort of the full takeaway of all the different sensors that we tried out and the models that we ran. From satellite here on the left, PlanetScope is a commercial company. Sentinel-2 is ESA public data. Some drone multispectral, so both the MicaSense, which is a 5-band, and the Mavic 3M, which is a 4-band. Full Vone imaging spectroscopy, so that's that full V-near to SWIR range, hundreds of bands of information. The in-field NDVI sensor, and then also field spectrometer data. So leaf clips are just like super good spectral data, but just on a small area on an individual leaf. It's hard to capture the whole vineyard variability in using that instrument. This is just meant for the industry advisors to get a look at all these different sensors, what they cost, what you get out of it, and my sort of recommendation. So I have this color coded by easiest and cheapest to hardest and priciest. So imaging spectroscopy is both the most difficult in terms of turning it into the numbers that you want and the most expensive. And as you can see by all these R squares on the bottom, it's not really any better than the other solutions. So that's should have a big X through it. On the other end of the spectrum, Sentinel-2 is free. So it's like a no-brainer to implement. If you have some management decisions you need to make and various spatial layers of information on your vineyard, you can easily add Sentinel-2 data as one of those. It's not the highest in terms of R squared on here, but it's not terribly different than what we're saying are our best solutions here, which is probably the field spectrometer. Again, this is not cheap by any means, but if you want the best information on an estimate of nitrogen or potassium or these other things, that's your best option. The orange are somewhere in the middle. I think the drones provide a unique role because you're actually able to extract spectral information throughout the whole field, but also of your target of interest. And you're able to access structural information about that target, which I think is very relevant for this discussion. These are just model output examples. So I'm showing the nitrogen and potassium for our drone-based multispectral, just so you could see, like I showed you R squares here, but here's the actual models. So all I'm doing is, all the bands available to the sensor. For the drones, I can add in canopy area, elevation, slope. These models are all assessed with tenfold cross-validation. And then also I'm showing the R squared for the held out test set that didn't see any, wasn't seen by the model in development. And then these are just support vector regression models. So I'm unsatisfied by these. Maybe you like these R squareds. I don't know. I wouldn't apply this to some unseen data and predict nitrogen content and just walk away and say, here you go, Mr. Viticulture farmer, use these. I'm unhappy with this. And I'm unhappy with this for a number of reasons. I've already sort of talked about the concentration numbers. I think that's not the target we should be going for. Now I'm going to try to explain why as best I can. So here I showed you through time, the nitrogen and potassium numbers. Here's just some simple vegetation indices through time from our drone data. So at the top are bloom and at the bottom are racin, and all of these are NDRE, which is just a normalized difference vegetation index using the near infrared and red edge bands. It's often used for estimation of nitrogen, maybe misguidedly. But anyway, here it is. This is the vegetation index. This is the spectral information. And here is canopy size information. So at bloom, I'm seeing just noise, right? Like there's no real trend in canopy area across the vineyard that I'm seeing stand out. But by the time you get to end of season, there's this very consistent sort of southwest to northeast trend that always seems to appear in this, band of like pitilly vines towards the southeast corner that always seem to show themselves. So I'm like, oh, this is probably related to nitrogen. This probably has an important role. How can we incorporate that? And actually, I went back in the literature, and it was there, like in those review papers on this from 2020. Towards the end, they talk about concentration versus content, and how the vast majority of remote sensing papers model concentration. And even some that say they're modeling content are actually modeling concentration. What content is providing some information about where the sample came from, right? So taking those concentration numbers from the lab and incorporating, the area that they came from. So when you take that sample, that leaf sample, before you send it off, you measure the size of the leaf, you weigh it, you determine, how much does this leaf weigh per square centimeter usually, and multiply that. So that's one good step, right? Get our N numbers from percent into grams per square meter. But I'm measuring at the vine level. I want to be able to make decisions on a vine by vine basis, not on like a leaf basis, because vines could have any number of leaves. So I wanted to take another step that I haven't seen done, and that was to incorporate, the area of the canopy itself. And then there's multiple layers in that area, right, of leaves. So there's something called leaf area index, which is this unitless quantity, which is just, for every square, area on the ground, what area of leaves do we have in that column? So it's a number from, 0 to 6 or so. For vineyards, we didn't take this data. It would have been great if we could take this data, because then we can turn our numbers into like an actual N mass, right? So we have X number of grams of nitrogen in this entire vine. That I can more model with remote sensing data. So we didn't, like I said, we didn't have all this data. Like LMA is the leaf mass area. We have a small sample of this. We can use an average number for that, but we didn't take leaf area index. This is really going to vary vine to vine in the same way that the canopy area does. But I was playing around a little bit with some of these numbers. This is just that equation again, and sort of an average leaf mass area that we had for our thing. But these are impractical things to measure across the field, but I think it'll be helpful to dig more into it. So here I'm showing the effects of including the area, right? So on top right, I have the N concentration, the numbers I've been complaining about, versus the vegetation indices. And we get, R squared, not as good as our model, with all the machine learning and whatnot, but not terribly satisfying, right? R squared of 0.46 and 0.31 for the different growth stages. But if I normalize these, both the vine, if I dilute that N concentration across how big the vine is, and if I dilute this average vegetation index number for those vine pixels across, it's fine. I get these great R squares. So if I just normalize by the area of the vine itself, you get a great relationship. I think that makes a lot of sense. Going back to the appendices from the wine grape production guide that, had guidance for your concentration levels of nitrogen, but they also had all these qualifying statements about if, your N is this much, but the vine size is excessive, do this. If the vine size is diminutive, then do this. And so they're already taking into account this information. So I think the answer is to include it in our analysis from the remote sensing aspect as well. So I see it as there being like two sort of options to do nutrition management properly in vineyards. One is the point and shoot sensor. That's what I think the advisory committee wanted. I think that's a really hard ask on its own without any contextual information about the size of the vine, let alone everything else going on in the vineyard that might vary across vineyards. It actually absolutely does vary across vineyards. So I think the real solution is this multi-layer defined management zone strategy. And this is really what the vineyard managers on the project have been doing all along. They took our estimates, but they didn't just use them in a vacuum. They included all these other layers. So this is a slide from Terry. So he uses this GIS online program called My Efficient Vineyard. And you can plug in all your data layers and do some simple clustering analysis and things to come up with zones. So he would always include soil, pruning weight, so like the amount of canes that he cut from the vineyard at the end of the year from the previous year's yield, as well as his canopy sensing from inside in the vineyard with his NDVI sensor. And he would throw in our vine nitrogen estimates or whatever nutrient that we were providing to him. My suggestion is instead of providing these vine nitrogen estimates in concentration numbers, we go ahead and actually just give him pick your nitrogen-related vegetation indices and divided by the area of the vine, or multiplied by the area of the vine. It doesn't really matter. To get another layer that's more contextual about how much nitrogen is actually in the vine rather than just some arbitrary concentration that's independent of the actual size of the vine. Come with your 3 zones. If you want to validate it, you can go use really expensive infield spectroradiometer with the leaf clip and get a good diagnosis of the nutrition. So these are some of the colleagues on the project, also in the sensor group, who focused specifically on that modality. And they came up with a pretty good model of turning that full rich spectral information you get from the leaf clip into nutrition information. Obviously, you're limited spatially, right? You can't take these leaf clip specters all across the vineyard and even all across a single vine, right? You're just getting a postage stamp on each vine. So you're taking a lot of liberty, assuming that things are representative with where you sample. But if you use your management zone map, you could choose maybe where you want to sample in that way. Or you could do traditional samples based on this map. So that was sort of our end recommendation. And I sort of just had the epiphany recently of, let's stop trying to model concentrations and start considering the vine area into the problem as well, which I think is really sensible. So the take-home message, I guess, is that best case scenario, you should construct management zones from a combination of unchanged free data, like elevation that you can get from the USGS, slope, soil, annual data, previous year yield. If you cut vine material out of the vineyard, that's probably important to include. This year vine size and any radiometric information you can get, any spectral data, I should say. Whether it be free data from Sentinel-2, or if you want to go advanced and get drone data and measure vine size in addition to the spectral data, that'd be great. But literally whatever you can do to add additional layers of contextual information is the best strategy. So rather than get a precise number on your nutrient values, maybe you just need a management zone map that you go in and check out yourself in the field and see what's going on. So yeah, you could follow up with target assessment with in-field spectroscopy, or just do lab analysis in the traditional way, building your sample from the leaves in each zone. I think the easiest recommendation is for public satellite imagery to be incorporated into these layers that vineyard managers might already be using. Pretty low-hanging fruit. But if you want to do more advanced things, you should, consider the size of the vine and different ways to measure that. Future research should consider nutrient concentration in the context of vine size. This is probably the most important thing that I'm trying to say here. That sadly we missed for the majority of this project, I think. And I sort of came to a realization of as we went along. I'm going to leave it there. Take questions. A lot, right? Sorry.
Question.
Yeah.
So can you talk us a little bit about how did you measure the vine size, especially a bit more into the 3D part of the vine?
Sure. Yeah, so basically we're doing something called photogrammetry, right? As we fly across the vineyard, our sensors taking images from different places, but often of the same object from different perspectives. So we're able to build up like a triangulation of each pixel in 3D space, or each component of the image in 3D space. So that's how we're able to take the images and make like a 3D visualization of it. It's advanced incredibly over the course of just this project, your ability to do this. What I'm doing here is actually quite simple. I'm just taking what's called the surface model raster of this 3D point cloud of the vineyard, and a terrain model, so all the bottom points on the ground, subtracting them to get this sort of canopy height model raster, and then setting a threshold to say like anything. It's easy in vineyards because they're the only thing that's like 0.5 meter and above. the ground in the vineyard. So it's easy to make a nice little threshold. You can also do things like incorporate the actual spectral information of the vines and set a threshold for, NDVI or something to like even get more, aggressive in picking just pixels that are sunlit vine canopy pixels. And all I'm doing is, I know the resolution of this imagery. I know how many pixels are in each of these little boxes that represent the vine. You add them up, you can get area. You take the height, you can, approximate volume. Obviously, it's like more like a convex hull volume than what is in reality or not. There's a lot of gaps in there, obviously. But it's a relative measure, right, of the size of the vine, not an absolute.
This might be sort of a dumb question. I'm not a great person. There are vineyards who are doing this within their own companies. So how do they would they go and buy one of these really expensive cameras and have a team of people that drive their vineyards to get all this information, or how does this get used in the real world?
Yeah, that's a great question. And sort of what we were trying to come up with our recommendations here. So I know people do this from airborne systems, but I can't tell you what, a lot of their stuff is black box. They're not going to tell you exactly what their model is. But I suspect it's the thing that I'm complaining about, and that it's a good model for their vineyard, but it might not be a good model for your vineyard, right? Like they have to learn information about your vineyard and tune to it. You're only going to be able to get such a good estimation. I bet you they're mainly based off of pretty simple vegetation indices. I don't know the degree with, which they're accurate.
So there's maybe not an industry that has developed that has drones and consultants that go and fly their drones over.
I think people have started. I don't know. Most of the folks that we talk to that run vineyards were like, we spend like a couple $100 a year on nutrient management. They don't want to spend a lot of money.
Then in California, there are private consultancy companies who do even like a drone flying, and then sometimes they also do airborne. So basically, it's like a flight, and then they will fly the whole patch, and then all the growers which are within that line of the flight, they get it.
Yeah. What I'm telling you here is that, for all my caveats about like, the satellite data in that pixel, it's a lot of mixed information, right? But it's still doing a pretty good job of estimating these concentrations. I think the no-brainer thing is to use free satellite data, but not on its own. Like with all the other layers of information that you'd expect to matter for nutrition, like soil and elevation and things like that. If you would want to get slightly better information, drone would be great, but there's definitely like a lot of work to be done to simplify turning that into useful information. We've done some of that, but I don't know that people want to pay to get that data necessarily. As far as like a provider who's going to go out and, you rent their time basically.
Okay, if there is no further questions, thank you, Rob. And have a great break, everyone.
This has been a production of Cornell University, on the web at cornell.edu.